Hello everyone. Today we are going to perform an experiment based upon the interference of sound waves using Michelson interferometer. And the aim of our experiment is to calculate the wavelength of the ultrasound from the measurement curve. From our basic knowledge, we know that sound waves are mechanical waves that travel through a material medium that can be solid, liquid, as well as gas. Sound waves are longitudinal waves that disturb the medium along its own direction of propagation. When sound wave traverses through a medium, it forms compression and rarefaction. These are basically the zones of high particle density and low particle density of the medium. When sound waves propagate through a medium, these zones also propagate along the wave. Now, based upon the frequency, sound waves can be categorized in three types: infrasonic, audible, and ultrasonic. For infrasonic sound, the frequency is less than 20 Hz. For audible sound, it is between 20 Hz to 20 kHz. And for ultrasonic sound, this value is greater than 20 kHz. Our today's experiment is based upon the study of ultrasonic waves. All of you can see the experimental setup. This is our optical table, which is 1 meter long. The major divisions labeled upon this table are in centimeter, which are further divided into 10 parts. So the minimum distance that can be measured upon it is 1 mm. For electronic connections, we have this ultrasonic unit. This is the transmitter that has been connected to the TR1 diode socket. It takes input supply from the ultrasonic unit and generates ultrasonic waves of 40 kHz that travels along the forward direction. Now, this is the translucent screen, which is a semi-permeable membrane that has been set up at 45-degree angle, which partially reflects and transmits the sound wave incident upon it. These two screens are hard reflectors at 90 degree with respect to each other, and they completely reflect the sound wave incident upon them. This is our receiver, which measures the varying intensity of the ultrasonic wave, and the analog intensity measured by this receiver is further provided to the ultrasonic unit through the BNC socket. This signal is further amplified and rectified and given to the multimeter. This is the multimeter which reflects the varying intensity of the sound wave. Coming to the arrangement of the setup, this transmitter and the translucent screen, they are 20 cm from each other. This screen and the receiver, they are also 20 cm from each other. This translucent screen and the hard reflector, they are 30 cm distant from each other. We have to be very careful about the alignment. These three should be in line with each other. This translucent screen and the hard reflector screen, they are also 30 cm from each other. The distances just explained on the actual setup are in accordance with this figure, and these geometrical distances ensure the avoidance of direct irradiation of the receiver by the transmitter. Let us discuss the working of this setup. So this transmitter generates the ultrasonic waves of 40 kHz. These waves propagate along the forward direction, and we are interested in studying the waves parallel to the optical bench. These waves from the transmitter are first incident upon this translucent screen and are then partially reflected and transmitted. So the sound wave which are transmitted through this translucent screen are incident at 90 degree to this hard reflector. After reflection from the screen, they travel into the backward direction and they fall back upon this translucent screen. So this is the zone where the forward moving wave and the backward moving wave, both of them superimpose and form a standing wave. And the wavelength of ultrasonic waves can also be found by studying the standing wave into this direction as done into a previous experiment. Anyhow, in this experiment, we are only interested in studying this reflected backward wave which is incident upon this membrane and is then partially reflected into the direction of the receiver and partially transmitted into the direction of the transmitter. We are interested in studying the reflected sound wave along the direction of the receiver. Again, coming to the initial point, when the ultrasound emitted by the transmitter was reflected by the screen, it travels along the direction of the second hard reflector, gets reflected and propagates into the backward direction towards the membrane. This is also the zone of standing wave, but again we are only interested in the reflected wave incident upon the membrane, which is partially reflected into the direction of the transmitter and partially transmitted into the direction of the receiver. Now we will discuss about the waves coming towards the receiver. So basically these are two waves. One is coming from the reflector screen 1 and second is coming from the reflector screen 2, and both of them will superimpose over each other to form a resultant wave whose amplitude depends upon their phase. The phase is dependent upon the path length travelled by the sound waves while moving along the hard reflector screens. Now what we have to do, we have to keep on changing the distance of screen 1 from the translucent screen so as to change the path length of sound wave along this direction, due to which the phase of this wave will also change. It will keep on changing the interference pattern continuously. Subsequently, the receiver will register successive maxima and minima due to alternating sound pressure. We will measure the variation of sound wave intensity received by the receiver through the voltage drop across this multimeter. Now, as we move the reflector screen along the optical table, it becomes very important for us to measure this distance very precisely. For this, we have a combination of a main scale and a circular scale. This is the main scale, which is in alignment with the meter scale on the optical table. This main scale is same as that of the meter scale and it also measures a minimum of 1 mm distance. This is the circular scale, which has 100 divisions labeled upon it. If we give it 2 complete rotations, the movement along the main scale is 1 mm. So we can say that for 1 complete rotation, the movement along the main scale is 0.5 mm, which can also be called the pitch of the circular scale. Hence, one vernier scale division measures 0.005 mm. Now we will start performing the experiment. What we will do, we will note down the initial position of the screen on the main scale and will move it further away from the translucent screen by rotating the circular scale. By looking at its alignment with the meter scale on the optical table, the initial position of the screen can be noted, and after movement of the screen, further distance can be added to the initial position. Due to change in the path length, successive maxima and minima will be registered by the receiver, which will be reflected in the multimeter. We will read the corresponding voltage change through this multimeter. Now the knob has been set up at 10 volts. So you can see it measures maximum of 10 volts and it has been further divided into major divisions like 1, 2, 3, 4, 5, 6, 7 volts. Movement of the screen causes change in intensity of the sound, and the corresponding maxima and minima in voltage can also be observed. Now see, this was the maxima at 3 volts. Now we are heading towards a minima. We have to note down all the changes in the voltage so that we are able to plot the curve of intensity change corresponding to the screen position. So now we are heading towards a minima. It is 1.6, 1.5. So it was the minima at 1.5. We have to note down the corresponding position on main scale and circular scale. So in this way we have to study the readings on the multimeter and note down all the position values corresponding to the change in the voltage drop across the multimeter, and especially we have to be very careful about the maxima and the minima position. Now we will look at our main scale and circular scale. Now this reflector screen and the translucent screen, they are 30 centimeter away from each other, and the position of reflector screen on the optical table is 46 centimeter, and the distance arrangement of the screen is completely parallel to the optical table, and this central position of this distance arrangement is in alignment with the position on the optical table, which is 46 centimeter. So we can say that initially this central position measures 46 centimeter. After that we will start moving our circular scale to observe the corresponding intensity change on the multimeter. Now see, the value of voltage on this multimeter is changing continuously. So we can see from here the corresponding maximum voltage position and the minimum voltage position. So just as an example, we will read the position on the main scale. So on the main scale 1 mm has been covered, and now we will look at the position on circular scale. It is 71. So 71 divisions have been covered on the circular scale. So we will write down the values observed on both the scales to reach at a final value after addition. So we will continue the same procedure of the screen movement through this circular scale and observe the corresponding voltage change in the multimeter, and correspondingly we will observe the screen position in the same way that we have just discussed. Now this is our table where we will list several values for screen position through main scale, vernier scale, and the final value that we had just discussed, and the corresponding voltage observed on the multimeter. So keep in mind that we do not have to only note down the maxima and minima position, but the in between values also, because we will plot the intensity variation versus the screen position. Now suppose this is our first minima, this is our first maxima, this is the second minima, and this is the second maxima, and corresponding to these voltages we will observe some screen position as well. Now we will observe the difference between two successive minima and similarly two successive maxima. So let us call this minima difference delta y and the maxima difference delta x. Proceeding in the same way, we will observe several values of delta y like delta y1, delta y2, and several values of delta x like delta x1, delta x2, and so on. Now this is a typical graph for voltage variation along the y-axis and the screen position along the x-axis. So we will find out several maxima position and several minima position. We will list out different measurements to plot this kind of graph, and after that we will find the difference between two successive maxima and minima, and in this way we will keep on finding this difference for several successive maxima and minima. So by plotting the graph, we will reach at this kind of table where we will attain the intensity maxima position difference delta x and intensity minima position difference delta y. So there will be several values of these delta x and several values of these delta y. We can average out the values of delta x and delta y to reduce any possibility of human error caused during the measurement. After that, we can also take the average of delta x as well as delta y to reach out at a particular value of delta d. So from our table for delta x and delta y, we reach at a particular value of delta d, and from this delta d we can find out the wavelength of the ultrasound through this relation. And for an ideal case, we can say that as the frequency provided by ultrasonic unit was 40 kilohertz and the speed of sound is around 343 meter per second, and at a particular temperature of 20 degrees Celsius we obtain lambda to be around 0.858 centimeter, which is 8.58 millimeter. So at 20 degrees Celsius the value of delta d should be half of this lambda, so we can say it should be around 4.2 mm for our case as well, but of course some degree of difference can be caused. Now we will discuss the precautions of this experiment. To avoid any kind of disturbance introduced due to reflection of sound by the walls, cupboards and different objects placed inside the room, we should try to carry out these experiments in bigger rooms, not in the narrow rooms. Also, we should not stand too close to the experimental setup because we can also be the cause of disturbance for the sound waves. The second important thing is to maintain the proportionality between the transmitter signal and the receiver's analog signal. We should avoid carrying out these experiments in saturation range. In that scenario, what happens? The overloading LED light of this ultrasonic unit glows. So we should avoid this case. The third important thing is that we should always read the values of the main scale, circular scale and the multimeter correctly. For this, we should always stand completely in front of the multimeter as well as the optical table. By this, we can also avoid any kind of parallax error. Thanks for watching the video.